Today we will examine a famous number, pi. Let's ask Mathematica what pi is and tells you pi is pi. That's not useful. I wanted to know the decimal expansion of it, so I asked it to tell me the numerical expansion of pi. Then it tells me this. My calculator knows this much. In fact, I know this much. So I ask for more of it. Give me 100 digits. And it gives me. I could ask for a lot more. I could ask for 1,000. And it would give me. It doesn't mind. You can ask for 1 million, but it goes for many, many pages. In fact, 1,000 times more than this. So do it at your own leisure. I will just demonstrate the concept with 100 numbers for now. Okay? Okay, now the question is this. Do all numbers appear equally often? That is, does it have more ones than twos or threes? How do you know? Can we go and count and see how many, which number has most counts? Which number appears more often? Let's do that. When all numbers appear equally often, we call the number normal. So this question, phrased with mathematical terminology, is pi normal? Pi seems to be normal, and we will see why we think that way. But we don't know because nobody has examined all the digits. We have examined something like along the trillion digits of pi. Up to there, it seems to be normal. But we have no way of predicting what next number will be, what the next digit will be, without actually computing. So it's conceivable, though unlikely, that after 1 trillionth digit, it will repeat 2 all the way. Who knows, right? So we'll examine this ourselves. Is it normal distribution? Is pi normal? Is what we want to know. Okay, but when it's written like this, we cannot go and count them. We can do two, and start how many of them there are. So what we have to do is that we have to count it by breaking it apart first. So I will do real digits of this number. And then it would tell me the same result all broken up into separate numbers. But here's this one extra number that tells me that this tells me how many numbers there are before the decimal point. Pi starts with 3.14, so therefore there's one digit before the decimal point. I don't want this number. I just want this what pi is made of. So what I do is that I get the first element of the list. First element. So it will give me the digits of pi. So I got what I wanted. Okay. I will call this my pi. My pi is not a number, it's a list that contains the digits of pi. So I will do Shift Enter, and I got that. Okay. But I don't want to count it myself, so I will tally it. And tally of my pi. Then this gives me the count. The digit 3 happened 12 times, digit 1 happened 8 times, and so on. Okay, I will store this result into my stats. So I have statistics of the pi. Now, if I plot this here, list plot of stats, I get this here. This is somewhat anticlimactic. The data seems so dinky. And if I do list line plot to connect the dots here, I get a mess because they didn't show up in order here. So I said, I give up. I don't want this. So what I do is I will sort them first. So I will call it ordered stats is my sorted stats. Okay, I got the same data as before, but this time it is in order. 0 appears 8 times, 1 appears 8 times, and so on. So if I do list line plot of ordered stats, then this time it looks better at least. But this still is very unsubstantial. That just doesn't look right. So we will give up on this plotting the line here. Instead, we will go with the bar chart, okay, of the ordered stats. Let's see. Then I get this complicated stuff because it's trying to plot both of them for me. It's trying to plot 0. It's trying to plot 8. 1 and 8. So I got 0 and 8. 1 and 8, 2 and 8. I don't want these. I would just want the second numbers here. I want to know that there are 8 of them, 12 of them, and so on. So I will extract the second numbers out of this ordered stats. So how do I do that? I will call it, this is the data I really want, so I will call it my data. Is out of ordered stats that I have here, I will get out of all of them, I will get the second elements only. And I got what I wanted. So I got 8, 8, 12, 12. So that's 8, 8, 12, 12. Okay, so instead of plotting those pairs of numbers, I will just plot the single array of numbers. There we go. So there's my chart. Obviously, this pi is not normal here. It's all jagged up and down. But I don't like this graph. It looks too simple. I want it to look fancier. When you make presentations, make the graph as fancy as possible. It's the same data, but when it looks better, you look better. And your research somehow looks better too. So here we go. Oh, it's 3D. Very nice. Okay, actually we can do better than that. First, let's give labels here. So the labels are, to save time, I typed it before. So I'll copy it in here. So labels are given this way, with this kind of syntax. So when you have labels, then you have all those numbers in front here. That's very nice. But you can also do more than that by changing the color and the shape of the bar chart. I will show you. I also pre-made them. Here we go. So when you use this here, the chart element function to be profile cube and chart style to be pastel, then you get profile cube, pastel, bar graphs in 3D. That looks like this. Oh, this is the same data as before, but somehow it looks so much advanced. So your research looks advanced. Okay. So this is the distribution of the frequency of how each digits come out on your pi. So I'd like to show you. Now let's start the research. I will just get rid of these outputs here. And also, I will suppress the output of each step of the way. Okay. And then what I will do is I will combine all of them into a single cell. I will right click and I'm clicking merge cells. Okay, so when I do shift enter here, I could just erase the output. It will regenerate. When I do shift enter, it will create it for me. So now I'm ready here. What if I have 1,000 digits here? Would the distribution be better? Oh, it looks more even. But 1 is very pronounced here, right? Now if I had 10,000, oh, it gets more even. And 100,000, 1 million. Wow, seems to be coming out pretty much evenly here. Okay, now is pi unique in that? What if I have square root? Is square root of 2 normal? Normal as in do all digits come out frequently, equally frequently? So when I do this, square root of 2, it appears to be. What if it's square root of 3? Indeed. So all these irrational numbers seems to be, I will skip 4. What if I do 4 here? Bam! Okay, the reason this seems to be 0 all the way is because your tally cannot tally the numbers that do not exist. Let me show you what I mean by this. When I do this here, I'll just do it with a few numbers here. It's made of 2 and then lots of zeros here. So the zeros are this here, and then this is 2. Although this says 1 here, it's just the first number. So what if I have 9 here? Of course, it will have just 3 followed by 0. Your graph would look identical even if it's 9 here. See, it's the same. If I have 25, and you will get the same result here. But anyway, going back to this, and if you make 26, it's an irrational number again, then you get this spectacular distribution that is almost uniform of this irrational number. So these irrational numbers that we examined now seem to be all normal. But as I said, we didn't examine all the way to the end, and we can't because these are infinite. So this is still a field of research and also an endless source of fascination for us. So next time you want to do any counting of digits that you want to do, this is the template you can use to explore your own.